How does entropy drive chemical reactions and phase transitions? Imagine a room filled with children playing with building blocks. At first, they might have the blocks neatly stacked. But as they play, the blocks get scattered everywhere, creating a mess. This messiness is similar to what scientists call entropy. Entropy measures the disorder or randomness in a system. The more ways the components of a system can be arranged, the higher the entropy. Now, let's connect this idea to chemical reactions and phase transitions. Entropy plays a key role in determining whether these processes happen on their own. According to the second law of thermodynamics, the total entropy of an isolated system tends to increase over time. This means that processes that lead to greater disorder are naturally favored. When a chemical reaction occurs, the change in entropy, often represented as deltas, works alongside changes in energy to influence spontaneity. The Gibbs free energy equation, which is delta equals delta minus T times deltas, helps us understand this relationship. Here, delta represents the change in free energy, delta is the change in enthalpy or heat content, and T is the temperature. A reaction is likely to be spontaneous if delta is negative. If the entropy increases, or if deltas is positive, it can help make a reaction more likely to happen, even if the enthalpy change is not favorable. For example, when a solid turns into a gas, the number of possible arrangements of molecules increases significantly. This increase in entropy often drives the reaction forward. Think about ice melting. The solid water molecules are arranged in a fixed structure. When ice melts at 0 degrees Celsius, those molecules become more disordered as they transition into liquid water. This increase in disorder raises the entropy and drives the melting process. Phase transitions like boiling also involve changes in entropy. When a liquid turns into a gas, the molecules gain more freedom to move around. This freedom increases the system's entropy, making it easier for the phase change to occur at specific temperatures and pressures. At the boiling point, the increase in entropy balances the energy needed to turn the liquid into vapor. Another example is mixing substances. When different gases or liquids mix, the number of possible molecular arrangements increases, raising the entropy. This can lead to spontaneous mixing without needing any heat exchange. In essence, entropy drives chemical reactions and phase transitions by favoring states with higher disorder. This tendency toward increased entropy, combined with energy changes, determines whether a process can happen without outside help. Understanding entropy in this way makes the principles of thermodynamics more relatable, linking what happens at the molecular level to observable changes in matter.